Jay Robinson. And she's currently attending Red Rocks Community College in biology, and she plans on transferring to a four-year university to continue studies in environmental science with an interest in sustainable living.
Thanks, Alicia. So I'm Jay, and I worked with Rick Saltus and Anna Liao in researching how accurately noisy smartphone data can capture a space weather signal using the application Crowdmag. In this presentation, I'll go over what Crowdmag is and how it's used to gather data on space weather via our planet's magnetic field. So Earth's magnetic field protects us from space weather, including solar wind, solar flares, and radiation. Solar wind, or coronal mass ejections, is the sun's magnetic field and plasma shooting from the sun at high velocities. Big space weather events can disrupt many systems, such as power grids, navigation, electronics, radio, and satellite operations. There's only a handful of observatories around the world collecting space weather data, so isolating a space weather signal from a smartphone would lead to not only finding the characteristics of the smartphone and how it acts in regards to solar storms, but also further studies into solar storms, so we can be better equipped to handle them. So Crowdmag is an app made to access the phone's magnetometer. And the magnetometer is basically just the phone's compass. It's used in GPS and navigation. Crowdmag maps the spatial variations in the magnetic field, which can be used to detect objects such as metal pipes that interact with the field. And this is done by holding the phone while mobile on any given path while data is being recorded. Clicking actually back one, Casey. That's the map page in the app that uses your location in the field to record the magnetic variations around you. But this project specifically was used to collect the time variations of the magnetic field. Solar activity is one cause of the time variations. And this is done by keeping your phone sitting in one place while recording data. And actually, if you go forward one, that's the graphs page, which gives visuals of the magnetic field coupled with the phone's noise, which is really helpful when the phone's stationary because you can see the variations in real time. Next slide, please. So this is a picture of an experiment attempting to use 7 Samsung Galaxies and 1 iPhone 4. If you go forward one, that's the iPhone 4 highlighted. It was the only phone in this experiment that was able to collect a sufficient amount of data points. But none of the phones could be used could be analyzed because of technical difficulties and or couldn't collect enough data points. So if you go to the next slide, here is plots of our first experiments involving gathering overnight data in Colorado with an iPhone 11 and an iPhone 12. And the iPhone 7 that we used isn't shown because that also couldn't collect enough data points. So the top column is June 18th and the bottom column is June 20th. And then the green data shown is iPhone 11 data, and the blue is iPhone 12 data. And then that last column is both together to compare. And what we see, we can kind of see in that red dashed box that there's some correlation, but overall, there isn't much correspondence. If you go to the next area, we can see the characteristics of the noise. The temperature is the long wavelength, which is the orange line, and the longer the data set is, the more distinct it is. There's also an example of a DC shift here, which is a sudden jump in data values that changes the average. And so if you go to the next slide, here's a diagram of iPhone 11 Crowdmag data gathered in Boulder over the course of 22 hours. You can clearly see the thermal wave in blue that contributes to the high amplitude variation. The noise itself, in this case, has a range of 600 nanotesla. The black trend is the signal, which varies from the thermal wave up to 100 nanotesla. Our conclusion from this analysis is that amplitudes greater than at least 100 nanotesla is needed to identify space weather variations. And the Boulder Observatory data is not shown in this because it didn't vary over that 100. So a space weather signal was not able to be obtained from this. If you go to the next slide, we have filtered data from Fairbanks, Alaska, courtesy to the geophysicist Abraham Inland, who collected this. This data is from a Samsung 7S Edge, which is shown in purple, compared with filtered Fairbanks Observatory data shown in blue. You can see there's a strong correlation between the signal, between the observatory signal and the phone signal. Although this is just the first steps, we know it's possible to get a space weather signal in noisy phone data with the right conditions. If you go to the next slide, we have the conclusions and next steps. So there's a lot of different ways this can be further explored. The main problem was that space weather in Boulder didn't vary over 80 nanotesla between June and July. And when closer to the pole, the space weather signal was more accurate, which is what we're aiming for. Working with more than one phone in areas near the poles would give the most ideal results. And working with more devices co-located specifically with newer battery lives in general would probably be the next steps to isolating the space weather signal. You can go to the next slide. So can a smartphone magnetometer detect space weather? Yes, sometimes, and part of our work is figuring out when those times are and filtering out the noise to make it happen. And then you can go to the last slide.
Okay. Is that the end of your talk? Okay, great. So we have time for one maybe question. Let's see. Okay. So do you think future phones will have better magnetometers?
I think depending on the phone company's goal, if they're more open to using phones for more scientific purposes, then yes, for sure. But citizen science, just using the magnetometers for GPS and not super precise events, I don't think that it's needed to be, oh my goodness, I'm sorry. It's not needed to.
No worries.
Yeah.
Okay. All right. And is there other equipment that you think might better help measure this?
Yes, like observatories are made to track space weather, but like everyone has a phone. So if we can just, with what we have in the phone right now, if we can figure out how to make that space weather signal stronger, pull that out of the noisy phone data, then that's the most optimal.
Okay. Great. Thank you so much, Jay.